Newton's method. This is actually similar to what we were doing in section 4.2, except that it repeats the process. In 4.2, we were using the tangent line to approximate a curve, and so it's the same. Newton's method is the same idea, except what we're doing is we're trying to find the roots of a function, and we make an initial guess, and we get a tangent line. So our initial guess is x1, and we use that to get a tangent line, and then to the graph, and then we see where the tangent line hits, and that gives us the second estimate. And then we can use that to repeat the process to get a third estimate or a fourth estimate. So the formula for doing this is x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. And you have to be a little bit careful with your choice of the initial point, because if it's too far away, if the function is sort of going up and down, and your point is not close to where it intersects the x-axis, then your initial your second point may be further away than your initial guess. So here's a picture that kind of illustrates this. Our x1 is here, and the slope is actually takes us of the tangent line takes us further away from where the graph actually crosses the x-axis. So you have to be a little bit careful about your initial choice of points. There's a rule of thumb for precision. If successive approximations agree on the first d decimal places, then our last estimate is accurate to d decimal places. So I'll go over some examples. This is the square root of 2. Remember, in section 4.2, we used linear approximation to estimate square root of 3. And it's sort of the same idea here. We want to write x is equal to square root of 2, and then square both sides. X squared is equal to 2, and then subtract 2 from both sides. And so our function is going to be x squared minus 2. F of x equal x squared minus 2. We can make an initial guess. 1 squared is 1, 2 squared is 4. So somewhere between 1 and 2 would be a good choice. We'll let x1 is equal to 1, just to keep things simple. Because the computations get a little messy here when you start working with fractions and decimals. So x sub 2 then is going to be x sub 1 minus f of x 1 divided by f prime of x sub 1. Okay, so let's compute f prime of x is going to be 2x. So this is going to be x1 is 1 minus f of x1 is 1 squared minus 2 is negative 1, and f prime of x1, 2 times 1 is 2. So double negative is positive. This is 1 plus 1 half, which is 3 halves. Okay, so x2 is 3 halves, and then we can then use that to get a third estimate. x3 is equal to x2 minus f of x sub 2 over f prime of x2. So it's going to be 3 halves minus f of x2 is 3 halves squared is 9 fourths minus 2 is 1 fourth, and f prime of 3 halves is going to be 2 times 3 halves, which is 3. So we have 3 halves minus 1/12, and multiply top and bottom by 6 to get a common denominator. 18/12 minus 1/12 is 17/12. So our third estimate is 17/12. And as you can see, the computations get pretty messy. Newton's method is it's hard to do by hand. It might be useful for a computer program to estimate roots, but the computation gets kind of messy. We went from a whole number to denominator 2 to denominator 12, and it gets messier the further you go. Okay, so another example, use Newton's method to estimate a solution to x cubed plus 2x equal 5. If we subtract 5 from both sides, that means that x cubed plus 2x minus 5 equals 0, and we can let f of x equal that function. F prime of x then is going to be 3x squared plus 2. And so let's make an initial guess here. F of 1 is 1 plus 2 minus 5 is negative 2. F of 2 is 8 plus 4 is 12 minus 5 is 7. So there's a sign change between 1 and 2. It looks like it's going to be closer to 1, so we'll let x1 equal 1. And then x2, our second estimate, is going to be x1 minus f of x1 over f prime of x1. So it's 1 minus a negative 2 divided by 5. 3 times 1 squared plus 2 is 5. So this is 1 plus 2/5, which would be 7/5. Okay, and then we do another estimate, x2. This is going to get kind of messy here, but let's do f of 7/5. So this f of x2 is going to be 7/5 cubed plus 2 times 7/5 minus 5. 7/5 cubed, 7 times 7 is 49, and then times 7 is, I think it's 343. 343 over 125 plus 14 over 5, and then minus 5. So we want a common denominator. 25 times 14 is 350. 43 plus 350 minus 625 over 125. So it's 343 plus 350, 396 minus 625, 8. So this is going to be 68 over 125. Okay, so then we could do f prime of 7/5. Is going to be 3 times 7/5 squared plus 2, 147 over 25 plus 50 over 25, 197 over 25. So x3 is going to be 7/5. Well, let's put the formula down. x2 minus f of x2 over f prime of x2. So it's going to be 7/5 minus 68 over 125 over 197 over 25. So it's going to be 7/5 minus 68 over 125 times 25 over 197. And 25 into 125 goes 5 times. And we need a common denominator, so we'll multiply top and bottom of the first fraction by 197. 197 times 7 is 49. 9 times 7 is 63, 67. 1 times 7 is 7, 13, 1379. And then 197 times 5. 35, 48, 985. Okay, so this is 1379 minus 68 over 985. 1379 minus 68. 1311. That's 1311 over 985. Okay, so that's our third estimate, and we could keep on going. I think probably Newton's method in conjunction with a computer program may be useful in some cases for some equations that are difficult to solve. I think doing it by hand, it gets pretty messy pretty quickly. Okay, so that concludes this presentation.